It is my pleasure to introduce our first speaker this afternoon. We have Marc Hoyois, I believe, to tell us about Motivic infinite loop spaces and Hilbert T.
Okay, yeah, thank you. So I refined the title of the talk a little bit. So let me rewrite it here. So Motivic, well, actually, infinite loop spaces of Motivic Thom spectra. Right, so I'm going to tell you about the infinite loop space of MGL, so that's going to be the main, and other Thom spectra. Okay, so yeah, before I do that, so let me remind you how this thing goes in topology. So recall, so in topology we have the Thom spectrum functor. We call it M. So this goes from spaces equipped with a map to the Picard space of the Galileo spectra. And this produces a spectrum for you. And so you get, well, there's tons of spectra you can construct this way, as many of you know, but some interesting ones, classical ones you get from the J homomorphism. So the J homomorphism is let's see, so I just start with the groupoid of vector space over the reals, finite dimensional vector spaces, and then I have a map to the Picard space of spectra, right? So this sends a vector space V to its one-point compactification. Yeah. Right. So. Oh, actually, let me remind you what this functor actually is. Okay, so this functor, what it does is, so if you have a map to this Picard space, so MF, or if the map F is undefined, I'm just going to write MX. So it's just the colimit of this map. So I just take the colimit over all x in x of f of x, right? And so that's a spectrum.
Mark, could you explain what pick of SP is?
Pick of SP, yeah, it's the, well, an object there is an invertible spectrum, so the sphere. Yeah, but I mean, this has all the higher homotopy. So in particular, the stable homotopy groups of spheres are. This information is contained in there. So this is a space. Yeah.
How do you construct it?
I mean, it's a subspace of the infinity category spectra. So I just start with the infinity category spectra and just restrict the objects to be the spheres, and then restrict the morphisms to be the invertible morphisms, and that's an infinity groupoid, okay, which is a space. Yeah.
And for you, everything's in the infinity category in most sense. So that co-limit is really some infinity category.
Yeah, so yeah, exactly. Yeah, yeah. Yeah, so I've pointed this out. Right, so the point, so I mean, the fact that we land in Picard is not particularly relevant for this definition. But this is useful because this is a group. Yeah, so if I have something, so a map like this, of course, this is a map of monoids. It takes the direct sum of vector bundle to the smash product of spheres. So because this is a group, this is going to factor through the group completion of this monoid here. So Right, so it factors uniquely to this group completion. And then, right, so this map I'm going to call little j. So now, for instance, you have that if you take the Thom spectrum of this map, J, which I'm just going to restrict it to the, right, so the objects there are kind of virtual vector bundles. So J0 means the restriction to just the rank 0 vector bundles there. And so this is a Thom spectrum MO, for instance. And I mean, you can get all the classical Thom spectra in this manner. So if you look at vector spaces equipped with some structure, so if you have some family of groups, some family of Lie groups, like the unitary groups or something like that, you can consider the group weight of vector spaces with the reduction of structure group to this thing. And again, this is going to factor to the group completion. And if you look at the Thom spectrum of this composite, that's the Thom spectrum MG. So like you get mu, m spin, or whatever in this manner. Okay, so now we have this this amazing theorem.
And I guess you get MUP, huh?
Yeah, okay. If I don't restrict to rank 0, I get the MUP. Yeah, exactly. Well, or right, for G equals U. Actually, for R, you just get one periodic spectrum. Yeah. Which, yeah, of course, this is just a kind of sum of Allenberg-McLean spectra, so this makes sense. But anyway, so now the theorem of Thom is that, right, so you take any, any map to BO. So yeah, so BO is the rank 0 part of this. The rank 0 part in there is equivalent to BO, so I'm just going to write BO for this. So if you have any space X mapping to BO, then you can consider Thom spectrum of this. And then the infinite loop space of that is a Bordism space of, oh, actually, I want a better statement. So I'm going to put an n-fold desuspension of this for some non-negative n. So then this is a Bordis space of n-dimensional smooth compact manifolds. With a stable X structure. So that means that the stable tangent bundle is equipped with the reduction of the structure group from BO to X. Right. So strictly speaking, I think, well, Thom proved a pi 0 version of this equivalence. Well, I'm also not defining what the right-hand side is, so I'm not going to do that. But you can define it in such a way that this is true. So I'm not sure that this actual theorem is written down in the literature. But yeah, the pi 0 version is Thom's theorem, and then Gautius, Madsen, Thielman, and Weiss, they prove kind of an unstable version of this, from which you can recover this like stable version from their result as well, at least for some particular x's. Right. So anyway, the goal now is to have a version of this in algebraic geometry. So that's what I want to talk about. So the goal. So algebra geometric version. Of this theorem. So what that means is that I just want to take the word manifold here and put variety instead. And well, instead of compact, I would say, you know, proper or something, but yeah. Right, so there is well, so there already is a theorem in that direction due to Marc Hoyois. Which is that, right. So this is for the case of the MGL spectrum. I'm going to actually recall, I'm going to tell you the definition of this a little bit later. So you take the underlying space of MGL, now again some suspension of that. Right, so it's a pi 0 statement, and if I take the pi 0 of this, then...
Mark, can you write bigger? I can't see what you've written.
Oh, okay, sorry. Yeah.
What does that suspension say?
Suspension minus n of MGL. Yeah. I don't have, okay.
But is minus n like minus 2n minus n, or what is what is suspension?
Oh, no, yeah, that was, it was too small, you didn't see, but it was minus 2n, come on, minus 2n. So, yeah. So this thing, so this is some Bordism group of n-dimensional varieties. Yeah. So, and actually here n can be, well, any integer. Right, so you might wonder what this means if n is negative, but I mean, this is really a kind of parametrized statement. Yeah. So for any, well, this thing here is really a pre-sheaf on like smooth varieties or something. So you can, you know, plug in any smooth variety, and then what this means then you should have to interpret this in parameterized settings. So it's really a family of varieties parameterized by some variety, and then it makes sense for the dimension, for the relative dimension, to be either positive or negative. Right, and also another thing is that this is in characteristic 0, so this is over some field of characteristic 0, we have this result. Okay. Right, so the theorem that I'm going to talk about is, well, so really the goal is that we just want to remove pi 0 here and replace the word group by space here. And well, we can't. We're not really close to being able to do that, but we can do it in the special case when n is equal to 0. So that's right. So case n equals 0. Maybe remove pi 0 or something, or the analog of Thom's theorem when n is 0. So in other words, it's going to tell you a description in terms of 0-dimensional varieties of the underlying space of these algebraic cobordism spectra. Okay. Right. So I think. Okay. So I need to tell you about Motivic Thom spectra. Okay, now I'm reminded that I forgot to say that this is joint work with people. Yeah. So this is joint work with Eldon and Manto, Adil, Khan, Vladimir Sosnilo, and Maria Jakobsen. Okay, so from now on this will be abbreviated like so. Right, so this Motivic Thom spectra, so this is a piece of like formalism that Tom Bachman and I developed. So we basically, we want to imitate this story here in the Motivic world, and it's very much formally the same. Kind of the only technical difference is that in the Motivic world, everything is like parameterized by the category of smooth schemes in some sense. So you just have to take that into account. So you have a Motivic Thom spectrum functor. Right, so my notation, okay. So I'm just going to write SPS for the infinity category of Motivic spectra over some scheme S. And then for this definition, I'm also going to need to consider SP underlined. So this will just mean the pre-sheaf that sends the scheme S to this category. Yeah. So the Motivic Thom spectrum functor now, so instead of spaces here, you're going to have some pre-sheaves of spaces on smooth varieties. And then with a map to the Picard space of the stable Motivic category, and the target is Motivic spectra over S. Right, and the formula for this is very similar to this one. So if you have, right, so if I have X, so now X is a pre-sheaf of spaces on smooth schemes. This is also a pre-sheaf of spaces, right? So because this thing is this pre-sheaf of infinity categories here. So if I have a map like this, so this means for every U, I have a map FU from XU, so it's some space, to the Picard space of spectra over U. I'll show you this family of maps. This is a natural transformation here. Then so the Motivic Thom spectrum of this is also just the co-limit of right. So now you have to take a co-limit to all U that are smooth schemes, and every point X in the space XU. All right, and then just take FU of X. So this is a spectrum over U, but I'm just going to regard it as a spectrum over S via the forgetful functor here. And then I just take this co-limit in spectra over S, and this is this Motivic Thom spectrum construction. Okay, so it's a very formal construction, but just like in topology, it recovers all the examples of Thom spectra. So right. So there's one more thing I have to mention, which is the J homomorphism. Yeah. Right. So Motivic J homomorphism. So again, it's the same, except everything is going to be parametrized. So you have vect. So now this is going to be some pre-sheaf and schemes. The pre-sheaf of groupoid, which to a scheme associates the groupoid of vector bundles over it. And then, so you have a map from there to this pre-sheaf of Picard spaces, and it sends also some vector bundle to this Motivic sphere SV. Right, and now you can play the same game because this is a group. This is going to factor through the group completion of this. And the group completion of vector bundles is at least over an affine scheme, is just the K-theory space. And even if it's not an affine scheme, I mean, we don't really care, but this thing is only this is Zariski sheaf, so so there's a map from the group completion of vector bundle to K-theory, which is an isomorphism on affine schemes. Yeah, so it's a Zariski local equivalence. Yeah, so it also factors uniquely through K-theory. Right.
Is S to the V the thing that people sometimes write T to the V?
Right. How? T to the V, yes. Yeah.
I mean,
Yes. the same.
I'm not advocating for the notation.
Yeah.
Would you use the notation sigma v in your case?
Sigma v. Oh, that's for the suspension functor or something. Yeah. Right. So then, of course, if you have some family of algebraic groups, like the special linear groups or the orthogonal groups, you can also, consider vector bundles with this structure, and you have some version of K theory for this, like oriented K theory or symplectic K theory, and again, you get maps out of this. And then if you take the Thom spectra of this map in this sense, you recover all the usual Motivic Thom spectra. So, yeah. Okay, so let me do this little table here. Right, so you have your map from X to K theory. Again, I'm going to just look at the rank 0 part of this. And the associated, well, let me not give a name to the map. So the associated Thom spectrum MX. So, all right, so if you take K theory itself, so the identity map here, you get the algebraic cobordism spectrum. So if you take this oriented K theory, so this you can define just as the fiber of the determinant. So the determinant is a map from K theory to PIC, but now this is a Picard group of line bundles in a scheme. Right? Yeah, so the fiber of this is going to give you the MSL Thom spectrum. And, well, there's many other examples. Let me mention one more, which is when you take X to be just a point, then, of course, you're going to get the sphere spectrum. Okay. Right. So now one kind of phenomenon which, where's the eraser? Phenomenon that you have in algebraic geometry, which is maybe a bit different, is the following. So if you have a variety, and so a variety is going to have a tangent bundle. So I want to put like structures on tangent bundles of varieties, right? Like as in Thom's theorem. So a variety is going to have a tangent bundle precisely if it's a smooth variety. But a variety is going to have a virtual tangent bundle. So for it to have a virtual tangent bundle, it suffices that it's a local complete intersection, which is like a significantly larger class of varieties. So, whenever you have a local complete intersection, you can ask for a reduction of the structure group of its virtual tangent bundle to something. So let me just make a definition with this. All right, so first, all right, so what is this virtual tangent bundle? So this is just the cotangent complex. And so a morphism of schemes, say U to V. So what does it mean for such a thing to be a local complete intersection, so LCI? So I'm just going to make my life easy and declare that a morphism is LCI if its cotangent complex is perfect. So the point of this is this allows you to regard, so any perfect complex gives you an element in K theory. Yeah? So this allows you to regard the cotangent complex as an element in the K theory of U. So this is the virtual or the stable tangent bundle, if you want. And then, so another definition that if you have a LCI map, and if you have Right, so if you have one of these pre-sheaves X mapping to, to K-theory, like this, so as we had over here, so then you can speak of an X structure on F. All right, so I mean, you should really think of this map as just a family of varieties parameterized by V. Everything has to be done in a parameterized setting. So this is really an X structure on the fibers of F, if you want. So an X structure on F is, right, so what is it going to be? It's just going to be a lift of, so you have cotangent complex that lives in KU. You have this, whatever space, you have E or X of U, so it's just a lift of the cotangent complex to this space. So what are some examples of this? For example, so if you take X to be this oriented K3 space here, right, so KSL structure, so that's a lift of the cotangent complex from K3 to oriented K3. If you look at the definition, this is the fiber of the determinant. That means that you have to give a trivialization of the determinant of the cotangent complex, also known as the canonical sheaf. So a KSL structure on F, this is the same thing as a trivialization of the canonical sheaf omega F. Right, so this is an algebraic version of being oriented. So another example, what if I take this sphere spectrum thing, so just like a point structure, so if you reduce all the way to the point, then, right, so this is just a point, so a lift of the cotangent complex here just means you have to trivialize the cotangent complex itself in K-theory. So this is what you would call a stable framing. All right, so it's a trivialization of the stable tangent bundle. Okay. Okay, so I think I can state the main theorem. Right, so this is a theorem over fields. Okay, is a field. Which might be a positive characteristic. So now take any map from some X to this rank 0 K theory. Okay, let me make sure I'm not forgetting any assumptions. Yeah. All right, no, there are no other assumptions. Okay. So, all right. So now take the infinite loop space of this Thom spectrum MX here. So this is a Motivic space, and it's equivalent to the following thing. So yeah, so proper zero-dimensional schemes with the X structure yeah. All right, so what I mean by this, So I mean the moduli space of such things, right? So this is supposed to be a pre-sheaf on schemes. So all right, so let me just elaborate on this. So this is a pre-sheaf that sends U to this kind of data over U. So that means a proper well, LCI is implicit because I'm using this notion of X structure here. So proper LCI map of relative dimension 0 with an X structure. Right, so just the moduli space of such things. And now there's one more thing that I need to do. So this thing, of course, is a group. It's a group like infinity space. This is a commutative monoid under just the disjoint union of such things. Yeah. So to get something which is like this, I actually have to take the group completion. Okay, I was using GP before for this. I have to take the group completion of this monoid. And then this will give me something which is equivalent of the Motivic space to this, the underlying space of this spectrum. Right, so maybe let me just make a remark on, so kind of the reason that we did this Thom spectrum business in the first place. So this was not related to this project here. So I mean, in topology, this Thom spectrum functor is kind of stupid. It's just the colimit, yeah. But the point of
Summarizing 40 years of algebraic recording.
right. So, but somehow the point of this is that this functor has excellent multiplicative properties. Yeah, so it's a way to build infinity ring spectra. For instance, if you start with, so this is a symmetric monoidal functor, right? So if you start with, I mean, even in topology or in this Motivic context, so if you start with if this map is an infinity map, then you get an infinity ring spectrum, for instance, or EN map or whatever. So this was kind of the motivation for us to consider this thing. And in fact, in this Motivic context, this is even more than a symmetric monoidal functor. It's also compatible with the norms that you have. You have finite étale norms on either side, and it's compatible with that. So if you have something which is like that has finite étale transfers, so if both of these, so this pre-sheaf has finite étale transfers, and if you have a pre-sheaf with finite étale transfers here, mapping to that, then the associated Thom spectrum will be what we call a normed spectrum. So this is the analog of the infinity G spectra that Magdalena and I talked about this morning in this Motivic context. So in particular, this is true for all these examples. So actually here, if you are in a case where this is an infinity space and this is an infinity map, then this becomes an infinity ring space. And if you think about this definition of X structure here, the fact that this is an infinity map will also makes this, will give this another symmetric monoidal structure given by the Cartesian product of these things. Yeah. And so then you can actually promote this to an equivalence of infinity ring spaces. And presumably you could do some norm thing, but we haven't looked at that.
Mark, why do you need to group complete in that
Oh yeah,
topological setting? You don't need.
Thanks for asking. Yeah, okay. So in topology, you don't need to group complete, and right, that's an excellent point. So so in topology, this thing is already a group because if you have 2 points, then you can write a cobordism like this to the empty manifold. Yeah. So the empty manifold is the 0 in this monoid. So. Right, you can do this kind of thing, which tells you that it's already a group. You can cancel things out. And the reason that this doesn't work in algebraic geometry, so if you want to think the algebraic geometric version of this picture, you have to think of this being the real points of some algebraic thing. And then, so this is, okay, so one difference in the algebraic case, we don't have the interval, but we can still consider the fine lines. Okay, that's fine. Just continue this a little bit. so this Boydism is supposed to be some proper map like this to the affine line, and well, it's not possible for such a thing to have an empty fiber. So the real points can be empty, but the complex points are not going to be empty, right? So in this case, here you're going to get like so if you work with the real numbers here, so these are some spec R's, then here you're going to have a spec C here. All right, so it's not possible to cancel out points algebraically. I guess that's the point, and this is why, yeah. So it's a key difference between with this and the topological situation, that you have to take the group completion here. Okay, so yeah, okay, so let me just point out the two examples, of course, that are of interest. So MGL, this is just the moduli space of proper, well, LCI zero-dimensional schemes. And then at the other extreme, if I take the sphere spectrum, I get the moduli space of proper stably framed zero-dimensional schemes. Right.
I didn't quite get that the space structure is on this proper zero-dimensional scheme. So you're not just considering it as a set, right?
Yeah, the groupoid of such things, yeah. So it's this presheaf of groupoid here.
So there's no higher homotopy groups or something.
Yes, right, exactly. Just, yeah. But I mean, of course, it appears when you do that.
But isn't X structure already something that has higher homotopy?
Oh, true, yeah, okay, yeah. It depends what X is, yeah. Fair enough, yeah. So, I mean, in the case of MGL, there isn't any because there's no X structure. So in this case, yeah, in this case, it will be an infinite groupoid before group completion, and yeah, but well, also in the oriented case, it's also just an ordinary groupoid, for instance, but yeah. Okay, and then, right, so there's one more thing. Well, so this is kind of very nice, but for geometric purposes, there's something kind of even nicer than this. So let me briefly mention this. So we can, so these moduli spaces are not actually representable by schemes, yeah. But you can change them up to, you know, A1 homotopy equivalents that they become representable by smooth schemes. And yeah, so you have, so if you do this, you get these Hilbert scheme models for these things. So for example, omega infinity MGL is going to be yeah, so you're going to take the Hilbert scheme of points in some infinite dimensional affine space, and so you look at those that are local complete intersections, right? So I mean, this is basically the same as this moduli space here. The difference is that to go from here to there, we choose an embedding of this zero-dimensional scheme in this infinite dimensional affine space. Well, it turns out that the space of such embeddings is A1 contractible, so it doesn't really make a difference. But the point now that we fix this embedding, this actually becomes, right, so this was previously a groupoid, but once you fix the embedding, it becomes a set, and it turns out it's representable by this scheme. And this is also a smooth, well, okay, it's an in scheme because of this infinity here, but it's a smooth scheme. Right, and of course you're still going to have to group complete this thing at the end. And for, yeah, okay, so for the sphere spectrum, we have a similar thing. This is representable by something which is like Hilbert scheme of framed points. So these are points in the Hilbert scheme together with a trivialization of the normal bundle of the embedding in this defined space. This is also a smooth scheme. Well, and other Thom spectra have similar descriptions as well. Just kind of change the decorations up here. Okay. So, okay, so let me talk about, let me kind of switch topics for a second to talk about Lurie's lemma. So, right. I'll tell you which one. No, but so, yeah, so I was lying somewhere. You may not have noticed. Where was I lying? Yeah, so I was lying because, right, so here's the issue here. So the definition of this Thom spectrum only involves, so X as a presheaf on smooth schemes, yeah, by definition. But, right, to talk about X structures and these things, right, so if you have some, okay, you have some smooth scheme U and you have some proper LCI, you know, relatively dimension your thing, then this V, you know, is almost never going to be smooth. So, well, I mean, so if X was only defined in smooth schemes to begin with, I have to tell you what X of V means to be able to have an X structure on this map. So this is the issue. Right, so V is not smooth. So what is X of V? I mean, if you believe the statements that I made, then in these cases, when the X structure is, when X is just the K-theory space, then X of V should just be the actual K-theory of this non-smooth scheme V. Yeah. And it turns out it does work out in this way, but this is kind of a not so obvious thing. So, right. Right, so this is a lemma due to Jacob Lurie, which says the following. So, if R is a commutative ring, so you can look at the K-theory functor from commutative algebras over R to spaces. Right, so this functor is left Gaussian extended from the subcategory, the full subcategory of smooth R algebras. Right. So it turns out that in this theorem, if you start with an X, which is just some presheaf and smooth schemes, and you want this to be a true statement, then you need to extend X to potentially non-smooth scheme via left Gaussian extension. That's the thing that's going to make the theorem work. So then to recover these statements here, you need to know that left Gaussian extension is what you want in all of these cases. And so this is the lemma that tells you that this is the case.
I mean, isn't this due to Vargas as well?
Oh, is it? I don't know. Yeah, maybe.
But.
Yeah, okay, so yeah, okay, let me give you the proof of this lemma because it's not, well, I think it's pretty cool. And maybe it's of interest to people who don't care about Motivic things otherwise. Okay, so right, so the first thing to note is that actually this is just a statement about finitely generated projective modules. Yeah, so because so this K-theory functor is just a group completion of this groupoid of finitely generated projective modules, if you think about, you know, the colimit formula for this left Gaussian extension, this is.
Can I just make sure I understand the statement now? So commutative ring, is this now actually a commutative ring?
Yeah. So yeah.
And commutative algebra, is this?
Commutative rings.
Is that actually a commutative algebra or no E infinity or?
Just discrete, discrete. Okay. It might be true for infinite things as well, but I haven't thought about that. No, just classical.
The left-hand side is the one category.
No, the right-hand side. So this is the infinity category of spaces.
Yeah, the left-hand
but this is
one
a one category of commutative R algebras. Yeah. Right. So the colimit formula is going to appear when you write down this scan extension is going to be a shifted colimit because tensor products of smooth R algebras are smooth, basically. So that means that this functor, of course, lands in infinity spaces, and that means the left scan extension is the same whether you consider the target to be infinity spaces or spaces. And once you put infinity spaces there, then this is just the group completion of just finitely generated projective modules, and group completion is like left adjoint, so it's going to commute with this scan extension. So it really is really a statement about finitely generated projective module. So this pre-sheaf of vector bundles that appeared before suffices to deal with vect. And all right, so what do we have to do to show that this is left scan extended? We just have to write it as a colimit of representables that are smooth. And so we can do that quite explicitly. So the first thing you can do is so this is a big disjoint union of rank n vector bundles, rank n. So it's a colimit, and then if you have vect n, what you can do is you can consider the Grassmannians of n planes, which maps to this groupoid. So now this is a pre-sheaf of groupoids, but this is just a pre-sheaf of sets. It maps there. And the difference between these two is that what this classifies is a vector bundle together with a family of generating sections. So over affine schemes, this is a surjective map, right? Every vector bundle, you can just choose a family of generating sections for it. So this as a map of pre-sheaves, this is like surjective on pi 0. And this is a smooth variety, so it's not affine though, so we would like to have, so it's not representable, but this is not really an issue. We can just take one of these Joannolu devices here. So that means that U of n is now an affine variety.
I can't read that. What does it say?
Joannolu device. Yeah.
What is that?
So it means that U of n is an affine variety, and this map is a torsor and a vector bundle. So you can always find such a thing for like a quasi-projective variety or something. And again, so if you over an affine scheme, any torsor under vector bundle is like trivial. So it has a section. So this is also a surjective map of pre-sheaves on affine schemes. And now this guy is representable, or it's a union of affine schemes. So now I'm just going to use the fact that if I have any map of spaces which is surjective on pi 0, then I can recover the target as a colimit of the check nerve of the map. So here I have a map between these pre-sheaves of spaces. Well, this is a pre-sheaf of sets, this is a pre-sheaf of groupoids, but it's surjective on pi 0. So that means that vect n is the colimit of the check nerve of this. And and now if you look at all the terms that appear in this check nerve, because UN is smooth, this map is smooth. I mean, this is an Artin stack with a fine diagonal or something like that. So all the terms, all the iterated fiber products in the check nerve are all going to be smooth affine schemes as well. So this explicitly write down this pre-sheaf as a colimit of representables that are all smooth schemes.
Mark?
Yes?
Yeah, it's believable for isomorphism classes of objects, but it's probably not true for automorphism.
This is a groupoid. Yeah.
Yeah, that's a groupoid, but I'm saying the colimit statement.
Yeah, no, it suffices to have a pi 0 surjection, and then this is always true. Yeah. Yeah. So. Okay. So maybe I'll try to tell you a tiny bit about the proof of this theorem.
Sorry, can you go through this slowly again? I didn't see why this was.
Right. So I just want to.
What is vect? What kind of object is vect?
Yeah, vect is a functor from commutative algebras over R to spaces, where you take the groupoid of finitely generated projective modules and take the nerve of it, if you will. Yeah.
That's not really the co-product that you wrote down in line.
Yeah, okay, it's a co-product for the perspective of connected varieties. Is that the objection?
Because you don't have constant rank necessarily.
Yeah. Yeah, that's fair enough. Okay. Yeah. So yeah. So maybe you need to argue a bit differently here, but I'm not going to be able to do it now. I don't have time. But yeah. I mean, is it clear otherwise?
Well, I mean, you can.
Yeah. Well, you can ask me later if you want more details on this. Okay, so yeah, so I just want to say something about the proof of this theorem. So somehow the base case of this theorem is actually going to be the sphere spectrum, and then all the other Thom spectra are obtained from this. Right. So, and this is where we use really this this formalism of Thom spectra that I talked about at the beginning. So we really write. We really want to write mx or as. So this is a colimit over all smooth schemes and all points x in xu of these spectra. Well, okay, in this case, because my x actually goes to K-theory, I mean, this x actually gives me a rank 0 K-theory class, so I'm just going to write this actual Thom spectrum. So this is a Thom spectrum of this rank 0 K-theory class on U. And then, okay, I can just take omega infinity here. Turns out you can commute it with this. So now you see that it suffices to understand this infinite loop space of this Thom spectra. Yeah. Right, so this C is really, yeah, okay. It's my name for this virtual vector bundle. Right, and so now well, you first look at the case C is just 0, so in other words, this is just the suspension spectrum of U. So you have to understand this thing. Right, and so then, okay, so this is kind of, well, the black box that I'm going to use for this sketch of argument. So this is just, well, it's a pre-sheaf on smooth schemes that sends V to the following pictures. So V, U, W, so there are spans like this. FG, where F is proper LCI of relative dimension 0, and we are given a trivialization of the stable tangent bundle. So this is happening in the K-theory of W. Right, okay, so this whole So this whole data is from the infinity groupoid, and this is this pre-sheaf, which gives you back this thing, again, after taking the group completion of that. Right, so this is a consequence of this recognition principle for Motivic spectra, which also, I mean, is based on work of quite a few people, so Garkusha and Panin, and Ananievsky, Neshitov, and well, this whole business of this kind of a framed correspondence goes back to Voevodsky. Right, okay, so I'm just going to take this for granted. So now I just have to tell you, well, how do you go from the case xi equals 0 to the case, to the general case? And so you can kind of maybe try to guess, you know, if you put a xi here, you know, how you modify the right-hand side in a sensible way, and your guess would be the correct answer. So if I look at this Thom spectrum, then so this is the consists of spans exactly as before. But now instead of saying that the cotangent complex is trivialized, now I have this xi that's here. So what I can say is that the cotangent complex is identified with the pullback of xi, right? So xi lives over u, I can pull it back to w, and this is where the cotangent complex is. Right, so this you can kind of, I mean, if you set up everything coherently enough, you can kind of deduce this from this. So the point, what you need to do is you basically need to identify, so there's actions of the loop space of K-theory on both sides. So here it acts via the J homomorphisms, and here it acts just by composing with, you know, a loop in K-theory there. Then you have to identify these two actions. And once you do that, then this is kind of a formal consequence of this. Okay, but now we have to take the colimit of all these things for all u. Sorry, this is a u, not an x. We have to take the colimit of these things for all smooth schemes u and all x's in. Well, let me just do the case where x is the K-theory space, so just the MGL case. So now xi is just rank 0 K-theory class in u. Okay, so we take this huge colimit here, and so what happens? So this cotangent complex is fixed, but now you take the, you know, the space. So this colimit is going to give you, like here, if you like xi vary, right, you get the colimit of all like paths from this thing to you know, an arbitrary point in the space. So of course this is contractible, which is the space of paths with a fixed endpoint in some space. Right, so actually to make this a valid argument, you need to know, so this xi is not an arbitrary K-theory class on W, so that's the issue. Xi is pulled back from U, so you need to know that there's enough, and U is a smooth scheme, so you need to know that there's enough K-theory classes on smooth schemes that you can pull back so that you can recover the whole K-theory space of W, and this is exactly what Larry's, the Bat-Larry lemma does for you. Right, so then when you take this colimit, everything disappears and you're just left with the map from W to V, okay, which is the answer for MGL. All right, so I'll stop here. Thank you.
Any questions?
Can you say something more why you can commute the omega infinity with the colimit in the first line?
Yeah, so this is because this is a shifted colimit, it turns out, and well, you have to prove that omega infinity commutes with shifted colimit, which is a non-trivial claim, but it also follows from this recognition principle. So because
It seems strange. I mean, in the classical case, when you write the Thom spectrum as a co-limit over just a space, there's no reason for the space. I mean, the space is two points, and that's not a sifted co-limit. So what's the
right, so it's the fact that this is parameterized over smooth schemes, I guess. Yeah. So,
Wait, I mean, is this a Thom spectrum or is it something not wrong?
I'll ask you later.
Does this help you with any particular calculations?
hopefully, in the long term. At the moment, yeah. So of course, something I didn't mention is, yeah. So from the computation perspective, well, you need to improve. I mean, so really, this I said this is like some Motivic equivalence or something. But if you want to, really compute the value of this on some field, it suffices to take the Suslin complex on the right-hand side. So just make this a one invariant, and that gives you the whole space over any field or any Henselian local ring, actually. So in general, it's an Isnevich hypercohomology of the Suslin complex on this moduli space.
So it's instead of cycles, it's schemes.
In some sense, yeah.
Okay, maybe we leave any more questions for later. After we're gonna have tea, and then we'll have one more talk. So we'll be back here at 4 o'clock. Thanks, Mark, again, please.